Hello everyone, today I'd like to present our paper titled NeuralScale, Efficient Scaling of Neurons for Resource-Constrained Deep Neural Networks. I'm the first author of this paper, Eugene Lee, advised by Professor Chen-Yi Lee. We are from National Chiao Tung University of Taiwan. First, we'd like to highlight the motivation of this work. When designing a neural network, we usually guess a lucky number for the neurons or filters, usually based on a prior experience in network design. Today we question the intuition behind this decision. Do we go from small to large? The design of this paper is based on three important ideas. First, from the paper, we're taking the value of neural network pruning. We know that pruning can be viewed as an architectural search method. Second, the low-ticket ticket hypothesis paper hypothesized and showed that there exists a subnetwork that learns faster than the original network and reaches higher test accuracy. Third, the paper EfficientNet shows that performance gain can be obtained if we exploit the relation among hyperparameters, for example, filters, layers, and input resolution. To answer the problem of neuron selection, we first come up with a hypothesis. Given a deep neural network with minimal redundant parameters, through the modeling of the change of neurons in each layer with respect to change in total parameters of the deep neural network, we are able to scale the deep neural network across various axes efficiently. To validate our hypothesis empirically, we formulate our problem as follows. We first perform iterative pruning using the approach from the paper, importance estimation for neural network pruning. We next parametrize the prune progress. Lastly, we scale our network according to the parameterization we perform. Before diving into details, we would like to show that through iterative pruning, the number of remaining filters across layers changes in accordance to the power law function with respect to the pruning iterations. Both plots shows the results of applying iterative pruning on DG11, where the left and the right plot shows the result for CIFAR100 and CIFAR100 respectively. You can see that for different datasets, the resulting remaining filters of each layer grows differently. To fit the curve shown in the previous slide, we propose a simple curve fitting method. We first lay out the notations. Tau is the total parameters, phi L is the neurons or filters of layer L. To model parametric growth, we perform curve fitting using power law. We model phi L as a function of tau, parameterized by two parameters, alpha L and beta L for each layer. We then linearize equation 1 by taking log on both sides of the equation shown in equation 2. We then formulate equation 2 into a matrix form which is composed of all layers in the network. The parameters theta, which is composed of alpha and beta, can then be solved directly using the least squares approach, giving us a neat result as shown in equation 4. Theta can then be used to generate architecture of arbitrary size, depending on the resource constraint of the hardware. An all-with approach, NeuralScale, is shown in the left figure. We first prune our network, followed by the parameterization of its progress, and finally, we can scale our network efficiently based on our parameterization. We then form a closed loop by repeating the entire process multiple iterations. We coin this method as architecture descent. The right figure shows a trivial case, which is through uniform scaling. Uniform scaling scales the neuron of filters of each layer using a fixed variable. The resulting architecture obtained using our approach is shown here. X-axis represents the iteration number of architecture descent, and Y-axis is the layer index. For all network dataset pair, we show heat maps corresponding to 4 ratios, 0.25, 3.75, 1.25, and 2. We can see the growth in the number of filters does not comply with the conventional wisdom of going from small to large, for the example of VG11 and CIFAR10 on the left. On the right, we can see the strata pattern for the heat map obtained using ResNet18 on CIFAR100, reflecting the design of residual blocks inherent in ResNet18. Here we plot the accuracy comparing NeuralScale with other approaches. The baseline is shown in red, uses uniform scale mentioned in the previous slide. The left plot shows the result of VG11 and CIFAR10. Improvement in accuracy between NeuralScale and MobileNetV2 is marginal here. The right plot shows the result of ResNet18 and TinyImageNet. Improvement in accuracy between different approaches can be observed more clearly in this example. In this slide, we conclude our presentation. First, our empirical result shows that through the nonlinear parameterization of iterative pruning progress, we are able to scale any network's neuron or filters efficiently. Second, this finding is important when we need to squeeze extra performance on resource-constrained devices. Third, NeuralScale optimates the flow of neuron or filter tuning process, reducing the engineering costs, or at least better than grid search. Thanks for spending your time listening to our presentation. Feel free to contact us if you have any questions. Our source code is released on GitHub. Feel free to drop by. I hope that our contribution will benefit your research. Once again, thank you and stay safe during this hard time.